Okay, so let's finish up the long drawn out activity where you arrange the pieces of paper that have those different characteristics on it. So hopefully what you've got is that you've got like hydrogen, which they don't know it's hydrogen, but it has atomic number 1, and then you've got that one with 4, and then coming down here like this, you have like the oxides that are 0.5s, you have the chlorides that are 1, okay? And all of these over here are going to be very high melting or boiling points, which means that all of these over here are going to be your solids at room temperature, okay? Then over here, kind of ish in this region, these are going to be your gases, okay? So like this is why we call hydrogen, helium, that whole column over there, or helium, neon, argon, we call them noble gases because oddly enough they're gases. And the reason that they're gases is that they don't form bonds with anything. So if you look at, and this is going to be important in terms of the lab that you can do today. So if something's going to form a solid, it's because these particles lock together, okay? And Mother Nature is a lazy prima donna. So if Mother Nature is going to go through the hassle of locking something together, it's because it goes to a lower energy state. And that's your overriding theme today. So when you look at any reaction that's going to take place, like for example, we're going to talk about forming precipitates or forming bubbles or something like that. If that reaction takes place, it's because Mother Nature, you remember like those energy diagrams? They said, oh, okay, right, here we go, right? They had those activation energies, right? And we talked about the roller coaster and things like that. So if Mother Nature ends up at a lower energy state, that's in her favor because she doesn't want to have to put effort into it. So when things are existing as gases, it's basically because when these particles bond with each other, they run into each other and they go, hey, you want to form a bond? And they go, nah, I'm good, thanks, okay? And so that's why they exist as gases. This is why we have an atmosphere. We have nitrogen and oxygen because nitrogen and oxygen are always running into each other. It's like, you want to form a bond? They go, yeah, good, thanks, okay? So they don't. So this is why it exists as gases. But some of them, like for example, all your metals, lithium, sodium, potassium, okay, all of those, when they hook up, they go, hey, you want to form a bond? They go, yeah, okay? And not only do they form a bond to make them a liquid, they form an even stronger bond that holds them together as a solid. So when these particles exist, like for example in the lab today, you're going to have chunks of aluminum, you're going to have chunks of magnesium, okay? And you're going to have these different chunks, okay? They exist as solids because when these atoms form bonds, they gain something from it. Okay, if they didn't gain something by forming together as a solid, they wouldn't. So, you should have a graph, and the graphs will be like kind of all over the place. So, you should have atomic number down here, okay, not the mass number, but the atomic number, okay, and that's going to go through 20. And if you did like the chlorides or the oxides, you should kind of get like a series of spikes, okay? And if you notice, and this is where it's actually kind of a linear progression, if you look at your chlorides, those actually go across, they go 1, if you do this right, the chloride's going to go 1, 2, 3, 4, and then they're going to start to shrink back down, and then they're going to go back to 3, 2, 1. So if you think about this as being like the slope of a line, oh, this is a linear graph. For every atomic, as your atomic number increases by 1, those chlorides increase by 1. So the slope of that line is going to be, oh, that's a 1-to-1 ratio. On the way down, oh, that slope is -1, because for every increase in atomic number, it shrinks by -1. So don't be afraid to take your mathematical knowledge of slopes and go, oh, that's linear. Oh, great, what's going to be the slope of that line? Your oxides do the same thing, but those goes by half. They go, oh, 0.5, 1, 1.5, okay? And then those show a similar type trend. If you graph melting point or boiling point, I don't care which one that you did, that kind of goes all over the place. That really doesn't follow like a trend because of the fact that you have so much of the periodic table that's solids, and very little of it is gas, and even a smaller amount of it is liquid at room temperature. So that's why those characteristics, you really can't say, oh, there's a trend. It isn't like boiling point goes up as you go across, or melting point goes up as you go across, okay? It really doesn't. So there really isn't a trend when it comes to boiling point or melting point, but there is a noticeable trend if you talk about the chlorides or the oxides, okay? Because that is a bonding with electrons, and that's why those tend to be periodic, and that's why it tends to be linear. The melting point and boiling point, there really isn't anything. So on that question, on that back, is either graph reveal a repeating cycle or cyclic pattern, okay, on your physical or chemical properties. And so on the chemical properties, you can say, yeah, there's a pattern, okay, it spikes and it goes back down. On the physical properties, and we're talking about, just so everybody's cool with the terminology, when you're talking about those physical properties, you're talking about, in this case, just melting point or boiling point. There are other physical properties you can talk about, like density. You can talk about what we call malleability, how easy it is to form it into like a shape of metal. You can talk about brittleness, is it hard, okay? You can talk about, is it soft, is it brittle, things like that. So that on that second question on the back, are these graphs consistent with patterns predicted from arranging the elements? Why or why not? So what you should see is that once you get your tables arranged, oh, there's a pattern that exists. Oh, your chlorides go from 1, 2, 3, 4, 4, 3, 2, 1. Your oxides go from 0.5. So in that regard, yes. So when you graph it, it's just a different way of looking at those same trends. So then it says, based upon these graphs, why is the chemical organization called a periodic table? Do not make this difficult. Just say, oh, the patterns repeat in a periodic trend. That's all you have to say. Don't make it complicated. And then, based upon your developed table, where would the element with a mass of 72 belong? Okay? So that you have that odd outlier. Okay? Let me give you a hint. Look at the chlorides. Okay? Look at the chlorides on that element with 72 and look at it in terms of that. Okay, so make sure on your graph that on the left vertical axis, make sure that you have told me whether you graphed chlorides or oxides, because those look completely different. And on the right side, make sure you tell me if you graph melting point or boiling point. Okay? Any questions on that one? Yes?
Do we need a title for the graph?
If you really want to get fancy, you could.
Okay, here's one.
Not mandatory, but generally you want to give a graph a title. In this case, you could put atomic number versus periodic trends. Something simple like that. Okay, are we good? Anything else? Going once, going twice, sold? Okay, so just hand in the paper by itself, the single sheet of paper, but then if you took the paper that has like the glued pieces of paper on it, put that on that table in the back, because I've got to grade both things, okay? So put the paper itself up in the tray, put the big paper on the back over there. Okay, so now let's talk about that sheet that I gave you yesterday on the periodic trend. So on this one, there's a couple of things that you kind of need to get in terms of first ionization energy. So first ionization energy, as the name implies, is the measure of energy, okay? So this one, in terms of trends that you can measure, is the easiest. So basically what you do is, like, if you want to measure the first ionization energy of an element, you basically put it in what we call an electric field. And the electric field has the capacity to pull those electrons away. So it's kind of like, let's say Miles has a piece of gum, okay? And Miles really likes gum, okay? And so if I'm talking about the first gum ionization energy, it would be how much energy that I have to exert to take that gum away from him, okay? Now, if he has a really, really strong attraction for gum, like, Mr. Kim, I love my gum. Okay, cool, right? So that means it's going to take me a lot of energy to get that gum away from him. Now, if he's like, hey, do you like gum? It's okay. Yeah, whatever. Okay? Then, it's not that big a deal. So when I taught this trend in Africa, all the kids there came from like agrarian farming background. And about everybody over there had goats. And so when I was teaching this in Africa, I would explain this in terms of goats. Are we recording this? Mm-hmm. Okay, good. I just thought about that. So it's like, okay, so the magic number of goats is 8. Okay, that's the magic number of goats is 8. So I said, okay, let's say you just had one goat, but to really get to being like cool, you need 8. So if you just have one goat, if I came up and was going to take away that one goat, and you only had one, would you hold on to that goat very strongly? Because not so much, teacher. Because if you only have one goat, okay, if you take it, great. If not that big deal. But if you had 4 goats, yeah, you're about halfway there, right? Like, I'd probably hold on to those goats a little bit stronger, okay? Now, I said, imagine if you had 7 goats, and you're only 1 goat away, they'd go, right, yeah. I'd hold on to those goats, because I have 7, but we need 8. And I said, now imagine that you have 8 goats. Man, that's cool, right? You're really, 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 really going to hold on to those goats. So, and you would hold them very, very tightly to you because, like, here's my 8 goats. So atoms and electrons kind of follow that same trend. So if you look at that chart, okay, on the back, and let's make sure everybody's cool with the terminology. So you talk about, in this, it's going to talk about groups, okay? So groups go up and down, okay? And so when it's asking about this, like for example, it talks about atomic radius and all these different things. So when you're talking about groups go up and down, periods go across. So if you look at this going across like this, okay? So if you look at this first ionization energy, okay, which is this second one down. So as you go across, and if you start like here with lithium, so this first period going across, lithium all the way over to neon. And it follows this beautiful trend. And so as you go across, that first ionization energy is getting higher and higher and higher because of the fact that you're increasing. There's a couple of trends that are going on. First off, the arrangement is getting closer to that magic number of 8, okay? Because that's what every atom wants to strive to have. Every atom wants to have 8 outer shell electrons, except for hydrogen and helium. They just want 2 because they're only filling that first energy level. So as you go across, you're getting closer and closer to that magic number of 8. So the atoms tend to hold on to those electrons even more because it's closer to that magic number of 8. The other thing that happens from the Coulombic forces standpoint is that as you go across, and that's that third number 8 is that atomic radius. So notice as you go across, that atomic radius is, as a general trend, is getting smaller. So think about what's happening. So as you go across from lithium all the way across to neon, And lithium has 3 protons, and over here you have neon, which has 10 protons, okay? And they're pulling on these electrons. Now, keep in mind, and this is vital that you get this concept, is that this is happening because these electrons are being pulled towards these protons. So, and each electron, we're not sharing this charge, okay? So, these electrons, this electron here is being pulled towards 3 protons. An electron here is being pulled towards 10 protons. And so as you're increasing the number of protons in that nucleus, those electrons are feeling a tighter and tighter and tighter pull. So if you think about this, okay, with an analogy with human beings, as if you like gum and that gum is halfway across the room, and I said, hey, can I take that gum? Yeah, go ahead, okay? I'm not going to have to fight you for it because it's so far away from you. But if that gum is sitting right here beside you and you really like that gum, it's like, hey, can I have the gum? It's like, no, okay, fight me for it. Bring it, try it, I dare you, okay? So then that would take me a lot more energy to get that gum away from you. So what you see is that as that atomic radius gets smaller, that first ionization energy is getting bigger because those electrons are being held more tightly. There's more protons in the nucleus. You're shrinking the distance. So it's going to take a lot more energy to pull those electrons away. Okay? So that's what you want to see. Now, those are pretty straightforward. First ionization energy, there you go. So you got a series of questions to answer. They're pretty straightforward. Now, when you get to this concept of electronegativity, okay? So electronegativity is what I usually refer to as like the Robin Hood trend, okay? Electronegativity is how willing an electron is to take an electron, how willing an atom is to take an electron from somebody else. So let's start with one idea. If you go over here and you look on the noble gases, helium, neon, argon, krypton, notice that they have no electronegativity values. They have atomic radius, they have first ionization energies, but they don't have electronegativity values. The reason that they don't have electronegativity values is because they're that cool. They don't need to take electrons in from anybody else. They're noble. They don't react with anything. They're like, hey, I've got the 8 goats. I've got a stable outer shell of electrons. I don't need to take electrons from anybody else, so quite frankly, I'm not going to. So if you can imagine a party, okay, and at parties, if you've been to parties, some people are very interactive. They're walking around, they're talking, hey, how you doing? They're high-fiving, okay. And you have other people that are like kind of chilling out, going, what's up? They're just kind of watching things go by. They're not really interacting. And so that would be the noble gases. So the noble gases are not going to interact with anybody at that party because they have the 8 goats, okay? They don't need goats from anybody else. Now, what you see is, if you look at fluorine, okay, which is like 4.0, and then you go down to chlorine, which is 3, and then you go down to bromine, which is 2.5, okay? So notice that those, especially fluorine, that's a very high value of electronegativity. Because if you think about it, so fluorine is sitting there, and it has 7 valence electrons, okay? So it's just like you have 7 goats. And if you get an 8th one, you're that cool, okay? 8 is the magic number. So fluorine is sitting there going, number 1, it needs 1 electron. So it's going to so imagine at this party, okay? This fluorine is going to go up to everybody going, hey, got an electron? Come on, man, I need an electron. Okay, need a fix. Come on, give me an electron. Give me an electron, okay? So these fluorines are, number 1, they're going to want 1 electron. The other thing that's happening is that fluorine is filling the energy level that's very close to the nucleus. That's why it really wants to pull that in. So fluorine, there's 2 reasons fluorine has a high electronegativity value. Number 1, it only needs 1 more electron, Okay, it doesn't need 2, doesn't need 3, it only needs 1 more. And then it becomes like neon, okay? So it needs 1 more, that's one reason it has a high electronegativity. The other reason is that it's filling the energy level that is closest to the nucleus, okay? And remember, as you decrease the distance, you increase that attractive force. So there's 2 things going for fluorine having a high electronegativity value. Now, chlorine also only needs 1 electron, okay? So that has that same trend. It has 7 valence electrons. Oh, it only needs 1 more. But chlorine is filling that 3rd energy level. So that's further from the nucleus. So it wants to take in an electron, but it's farther away. So it's like, yeah, I want to take one in, but I just don't have a strongest pull because it's further away. Then you get down to bromine. Bromine's going, dude, I need 1 electron, but it's filling that 4th energy level. So that's even further away. Now, here's the odd thing about electronegativity. It's measured in what units called Paulings. Okay, it's named after Linus Pauling, who was a physicist who came up with the scale. But here's the problem with electronegativity in terms of like how you actually measure it, is that we can't measure it directly. Okay, we can't. So what we do is it's kind of a relative scale. We said, okay, hey, you know, fluorine, that's really going to gain electrons because we know what we know about its electron arrangement. So we can't have like an electronegativity probe, okay? So if you Google, oh, I want to buy an electronegativity probe, you can't, okay? They don't exist. So it's a number, but there's no direct way to measure it. So here's what I want you to see in terms of electronegativity. As you go across, electronegativity gets bigger until you get the noble gases, and then it just stops, okay? So going across, electronegativity gets bigger. Going down, electronegativity gets smaller, okay? And that all has to do with atomic radius and getting to 8 goats, okay? Look at atomic radius. As you go across, atomic radius gets smaller, which is somewhat counterintuitive because a lot of people tend to go, oh, you're putting in more electrons, that should get bigger. But again, keeping in mind, each proton or each electron is fueling that pole. So you're putting more and more protons in that nucleus, and it's pulling on those electrons more. That's why that cloud is shrinking. So atomic radius, as you go across, it gets smaller. As you go down, it gets bigger. And the reason as you go down, it gets bigger is because you're adding layers to an onion. You're filling those outer energy levels, okay? So atomic radius gets smaller as you go across, it gets bigger as you go down. The electronegativity gets bigger as you go across, it gets smaller as you go down, okay? First ionization energy follows the same trend as atomic radius. So first ionization energy gets bigger as you go across and smaller as you go down. Okay, that's the whole point of this exercise, is that you look at those trends. Okay? Any questions on that? We're good? Going once? Going twice? Sold. Okay, so get those handed in. Now let me hand out the lab. Miles, you shut off that camera.
Okay.
All right. So what we're doing now is a continuation of this whole idea of trends and how things react. So when you look at what we can figure out with atoms, here's where we're limited. We can't actually watch things bond together. It isn't like, hey, wow, in physics, we're going to take a rocket and smash it into an asteroid, try and change it, trying to alter its projectile, its path. That's something that we can see, right? We can't watch reactions take place. We can't see an individual an electron, okay? We can't. They're just too small. Because, here's the classic example. Across here, there's 94,000 aluminum atoms, okay? I can't watch a single one of them react with something else, okay? It's not there. We can't do it. So what we do is we make what we call macroscopic observations. We watch for trends in how they react with something else. So here's your overriding theme as you go through this. Mother Nature is a lazy prima donna. So if you see a reaction taking place, it's because Mother Nature gains something from that, okay? And if you don't see a reaction taking place, Mother Nature is like, I'm good, okay? Nothing's going to happen. It's good. Not worth the effort, okay? But if she does make a reaction happen, it's because Mother Nature basically is generally going to end up at a lower energy state, okay? Mother Nature is going to gain something from that. So here's the deal. So when you look at these alkaline metals, okay, lithium, sodium, potassium, so you have to understand fundamentally how metals like lithium, sodium, okay, so lithium, sodium, potassium, okay, all of those react by losing electrons, okay? Very first day you all were in here, I did this reaction. I took a little piece of lithium, and I took a little piece of sodium, and I dropped it in water and reacted very vigorously, okay? And we store those elements in oil because of the fact that we can't store them in water because they react very violently with water. So basically what happens is that you look at the structure of lithium, 1s2, 2s1, sodium out here is 3s1, potassium out here, it has 4s1. Okay? So basically these elements are sitting there, God, it's like we have this extra electron and it's just annoying. Okay? It's like you're going out on a date and you've got to drag Timmy, your annoying little brother, with you. And it's like, really? Okay? Okay? So you're going to be more stable if you get rid of Timmy because you don't have to keep an eye on Timmy. So lithium, sodium, potassium, all the metals generally react by losing electrons. Okay? Because they only have like the one goat. And it's like, I only have one goat. It's like, I don't care. Somebody wants it, take the goat. I don't care. Okay? Now, on the other side of the spectrum, you have your nonmetals. Like, for example, fluorine. Okay? So fluorine is out here, and it's 1s2, 2s2, 2p5. Okay? Now, fluorine is sitting out here. Fluorine has 7 goats. It's cool, right? It's like, God, if I can get one more goat, okay, then I'll have 8. I'll be cool, right? I'll be looking like the noble gases. So, nonmetals react by taking in electrons. Metals react by giving up electrons. So if you start with that idea, fundamentally how things react. Metals give up electrons, nonmetals take in electrons. And so the reason that lithium, sodium, potassium, the reason that they don't exist in nature, like, don't go walk around, it's like, oh man, look, I found this chunk of sodium laying on the ground. No, you didn't, okay? Sodium is not going to exist as pure sodium because sodium wants to react so quickly and give up those electrons, okay? Now, on this question about calcium and magnesium, one of the things why we can't put that down the drain is because what you'll see in this lab is that magnesium and calcium react with water. So when you get done with this lab that you're going to do, you're going to have little bits of magnesium, little bits of calcium. Don't wash them down the sink, okay? Because they're going to react with the water that's down in the sink, and it's going to produce gas, and it's potentially flammable and things like that. Okay, so here's what you're going to do on the first part of this lab. So you're going to have this chart, okay? And you're going to take calcium, magnesium, and aluminum, okay? They're going to be in little jars over there. And you're just going to take one of those, and you're going to have a test tube, okay? And you're going to take a little chunk of that, and you're going to put it down there in the bottom. And you're going to add 20 drops of deionized water. And the reason that we use deionized water means that the ions have been taken out. So the only thing in there is just water. So therefore, there won't be other elements that could cause a reaction. So it's just going to be just with water. So, for example, you can take calcium, and later on, we'll talk more about this whole mechanism. But basically what's going to happen is that you're going to get calcium hydroxide and hydrogen gas. So basically what happens is that the calcium comes along and it has that water, okay, which we all know is like, here's your oxygen and here's your 2 hydrogens. So basically the calcium comes along to one of the hydrogens and it says, you, get out, okay, it's like a dance. So calcium shows up, oxygen is dancing with the 2 hydrogens, and the calcium goes, so, okay, I'm a great dancer. So it kicks out one of the hydrogens. It doesn't kick out both of them. It only kicks out one of the hydrogens. So you form this stuff, which is called calcium hydroxide. Okay, calcium hydroxide, things that have hydroxides are bases. Okay, you have acids and you have bases. These are bases. Hydroxides are bases. And then you form these bubbles of hydrogen gas. So what you should see is that when you drop in that piece of calcium, and then you begin to add the water to it, you should see bubbles begin to form, okay? And one of the things you're going to add to it is this stuff right here, which is called universal indicator. Universal indicator is what we use to determine if something is an acid or if something is a base or if it's just neutral, okay? So water is neutral. Water is neutral because it has an equal number of what we call hydronium ions, which are H pluses, and an equal number of hydroxide ions. So water has hydronium ions and it has hydroxide ions, but everything's just in balance, okay? So it's neutral. If something is an acid, it has a lot more hydronium ions. So one of the things you're going to use is, where is it at? Should be hydrochloric acid. So hydrochloric acid has a lot of hydronium ions, okay? So that makes it an acid. If something is a base, it has a lot of hydroxide ions. So that's the short version of an acid-based lecture. For now, something is an acid, you can look at this and go, oh, it has a bunch of hydronium ions in it. If something is a base, it has a bunch of hydroxide ions in it. So this is the simplest definitions of acids and bases. So what you should see is that you're going to have this universal indicator, and you're going to have these little cards in here. And based upon the color that this changes, it will tell you what we call a pH scale. So a pH scale indicates if something is an acid or a base. So the short version, again, of this lecture, which takes like 2 days. If your pH is below 7, that's an acid. If your pH is above 7, that's a base, okay? So right here where it says pH of 7, that's just kind of like this nice kind of middle green. That means the solution is neutral. You have an equal number of hydroniums and hydroxides. If something's acidic, it's going to turn red. If something's basic, it's going to turn purple, okay? So when you add this stuff to it, basically you're going to look at that color. After you add, so here's going to be your sequence. You're going to take your test tube. You're going to add in a chunk of calcium, okay? Excuse me, you're going to add just pure water to it. You're just going to have water. You're going to add a little bit of universal indicator. You're going to see what color it is. Then you're going to drop in the metal, let the reaction take place, and then you're going to see what color it is afterwards, okay? So you're going to have pure water, add the universal indicator, see what color it is, add the metal, let the reaction take place, see what happens to the color afterwards. Okay, so you need the before and after. Then you're going to do that with magnesium, and you're going to do that with aluminum. So here's the deal. So when metals react, if they react, they produce hydroxides. Hydroxides are basic, and the solution should turn purple. If nothing happens, if you drop something into water and nothing happens, that's cool. Like for example, I'm guessing you all have done dishes, right? Okay? When you put the metal that composed of your knives, your forks, your spoons, when you put that in water, does a reaction take place? No, that would be weird if it did. It's like, oh, I got to do the dishes, right? We're going to put the fork in the water and we're going to get this reaction that generates hydroxides and hydrogen gas, which would be cool, don't get me wrong. I want to do the dishes tonight, but it's going to be horrible for your parents because they're always going to have to be buying new silverware because every time you do the dishes, there's a chemical reaction and it dissolves in the water. It's cool, but it's not very cost effective in terms of the reaction. Okay. Now, the other thing that you're going to do is that you're going to take 20 drops of hydrochloric acid, put that into a test tube, and mind you, you're washing these test tubes out in between each reaction. And you're going to have 20 drops of hydrochloric acid, HCl, okay? Drop in about 20 drops. And don't have to sit there and count. Like if you get to 21, don't go, oh man, I got to start over. I added one too many drops, okay? No, add about 20 drops, okay? If you add 21, it's cool. Don't worry about it. Now, 30, that's a bit over the top. But if you flip out and go, oh man, I added 21, it's okay. Don't worry about it, okay? So then you're going to drop in this piece of calcium, okay? And then it's going to form a pretty vigorous reaction. And then you're going to have a match over there, and you're going to take that match after the reaction goes for a while, and take the test tube, kind of hold it like this, and you're going to take that burning match and you're going to put it inside of there. So if you generate hydrogen gas makes a very distinctive sound when it catches fire. It's like a popping sound, okay? It's called making the test tube pop. So there's two ways that you can tell, like, if this reaction takes place. If you're generating hydroxides, you can generate, if you do this, you form hydroxides and it'll turn purple. If you're generating hydrogen gas, you put a match in there, you'll get a popping sound, and that's how you know that you're generating hydrogen gas. Because hydrogen gas is the only gas that makes that distinctive sound with a match. Okay? So, obviously, if you drop the metals in there and no reaction takes place, don't worry about doing the match test, because there's not going to be any hydrogen in there to react. Okay? So don't worry about it. All right. Now, the second part, okay, over here on the back side. So what you're going to do there is that you're going to take this, which is known as a well plate, and because we're going over Miss Schultz's room, and by the way, make sure again, y'all know the rules, okay? Any matches, things like that, when you walk in, you see how those countertops are. When you get done, you see how those countertops are, and you leave them clean. Now, one other thing. On this one, you need the initial and final temperatures with those reactions. So you're going to have the handy-dandy little radar, like the temperature guns. So just shine that on the test tube before, shine it afterwards. That's the simplest way. It actually gives pretty decent measurements. So that's how you're going to measure the temperature of those before and after. Okay. And then you're going to do the match test, and you're going to make observations. On your observations, not only do you want to record if a reaction took place, you also want to record how vigorous the reaction was. Some reactions you'll see are going to take place. It's going to take a while for it to happen. Other ones are going to start taking like, boom, going to start a reaction. Okay? Now, over here on the other side. So what you're going to do is that you're going to react these different chemicals. So this is like a matrix. So you're going to mix sodium carbonate and magnesium chloride. So in the well plate, this is what I would recommend. And I don't care, there's two different thought processes. I don't care, pick one. So you know you're going to react magnesium chloride with sodium carbonate, sodium sulfate, and potassium iodate. Okay, that KLI3, so just so you know what it's called. So you have, obviously that's potassium. Okay, you're cool with this. This IO3 is an anion called iodate. okay, which is just kind of fun to say. So this is potassium iodate. So what you're going to do is that you're going to take magnesium chloride, which is going to be in these little dropper bottles. There's my magnesium chloride, there's strontium, barium, sodium. Love of God, where's my magnesium chloride? Why is there not magnesium chloride in here? Oh, it is. Okay, so this is what I would recommend. So you got this chart, right? So you need to react magnesium chloride with sodium sulfate, with sodium carbonate, Na2 with sodium carbonate, Na2SO4 with sodium sulfate, and then you have potassium iodide. So what I would do if I were doing this lab, and you don't take, it only takes about 5 drops of this. So I'd add about 5 drops like this, boom, 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 okay? So now I've got my magnesium chloride like this. Got this, there's my magnesium chloride. Then I'm going to add, for example, the sodium carbonate. So then I'm going to grab the sodium carbonate, it's labeled Na2CO3, and then I'm going to add some drops of that. Okay? So then I'm going to make an observation, and I'm going to look at this, and in this case, it's going to form just a tiny, tiny little bit of precipitate. So with this one, like this precipitate, it's kind of turning a little bit cloudy. Some of these precipitates are like really, really heavy, thick precipitates. Other ones are a little bit sketchy. They're kind of hard to see. So what I would do here, okay, where I've got my sodium carbonate and the magnesium chloride, it formed just a little bit of precipitate. Not much, just a tiny, tiny bit of precipitate. Now, you have to understand what's happening like on an atomic level. And this is a whole long lecture. I'm going to give you the short version of a very long lecture. So these are all soluble. If something's soluble, that means it dissolves in water. So how this is existing is sodium ions and you have carbonate ions, okay? And these have a charge of 2- because they've gained 2 electrons and the sodium has lost an electron. So within this, these that are existing as these little ions that are floating around. Then you have the magnesium chloride, which is also soluble, okay? So these things are floating around. So these are existing as individual ions. So it's like a dance, okay? So everybody's kind of dancing off by themselves going, okay, right? Everybody's chilling out. So then we're gonna mix these 2 dance parties together. And so the sodium is going to be attracted to the chlorine. So why is the sodium going to be attracted to the chlorine? What do you know about the charges?
Positive and negative.
Positive and negative. So the sodium goes, sup, okay? I got a positive charge. The chlorine goes, hey, I got a negative charge, right? And they're going to be attracted to each other. And the magnesium is going to be attracted to the carbonate, okay? So basically what happens is if you form a precipitate, that bond makes them come together. And they're going to go from being individual ions and going, oh, sup, okay? And then they're going to clump together, okay? So a precipitate is caused by these oppositely charged particles forming such a strong bond that they go from being individual dancers to now we're a couple. So when you see a precipitate form, it's because, again, Mother Nature gains something from it. So Mother Nature goes, hey, this is going to be more stable as dancing partners hooked up as opposed to these people existing separate. So with this one, this formed, and so what I would write here in this cell, okay, where you have the magnesium chloride and the sodium carbonate, I would write in here, formed a slight bit of precipitate, okay? Now, if you compare that with the potassium iodate, so now I'm going to grab some potassium iodate. Where's my potassium iodate? By the way, when you lay this out, I organize this. These are just going to be in tubs, so you're not scrambling trying to find this one. Now, if I do the potassium iodate with this one, that one stays like completely clear. Okay, if you look at this one, there is absolutely no precipitate whatsoever. So basically what happens, Mother Nature goes, hey, I'm cool. I'm going to keep everybody as separate ions. I'm not gonna make these things join together. Even though they're attracted because they have opposite charges, they're just not gonna hook up. They're just gonna be cool. It's like, okay? That's all. They're not gonna actually form anything. So when you see a precipitate form, it's because Mother Nature goes, wow, I'm gonna make something, lock these things together, and now they're not going to exist as separate ions, okay? Got the idea. So, this is, and these well plates are going to be numbered, like they're going to have like little numbers on them, like 1, 2, 3, 4, okay? What you'll notice, every one of these solutions that you're going to deal with, except for universal indicator, they all are clear. So what you want to do is lay out a thought process that says, okay, hey, what do I have? How do I know which reaction is taking place? So that's why you can do this one of two ways. You can take your sodium carbonate and put that in 4 solutions going across. So in other words, you can take that, go, oh, I'm going to put that in 4 well plates, and then I'm going to add the magnesium chloride to it, the calcium chloride, the strontium chloride, and the barium chloride. I don't care how you want to think this through. You want to put like all 4 at a time and then do the 3, or do you want to do the 3 and then add the 4? I don't care, okay? But here's what you want to observe. Is there a precipitate? If there is a precipitate, is there a lot of precipitate, okay? So like with this one, with this magnesium carbonate, I would write slight precipitate. And and precipitate is abbreviated PPT, okay? So that's the short version of precipitate. So if I were filling this chart out, I would write slight PPT, okay? And if there's nothing, you can just put an X or just put a dash or write no PPT, whatever that you want to do. This doesn't take very long, as long as you have like a good organizational scheme going, okay, we're going to do this, we're going to do this. Now, on your unknown, okay, so here's how we're going to do the unknown part of this, okay? So your unknown is either going to be, in this situation, you're going to answer these questions. So say down here on number 6, use results in part B to deduce the identity of the unknown alkaline earth metal. So here's what's going to happen. Let's say that I'm on one side of the table and Ella's on the other side. So what's going to happen on your unknown part of it, Ella's going to give me her set of her well plate, okay? And I'm going to maybe go to the other side of the room, or at least turn away, and I'm either going to grab magnesium chloride, calcium chloride, strontium, or barium, and I'm going to put that in the 3 well plates, okay? So let's say, for example, I'm going to pick magnesium chloride, okay? So this is what I'm going to do. I'm going to pick magnesium chloride so that Ella can see if she can figure that out. So what I'm going to do is that I'm going to take this and I'm going to put some of that in the 3 well plates, okay? So I'm going to know what it is. I'm not going to tell her, okay? I am going to go somewhere, turn around, do something so she can't see what I've done. So then I'm going to take this and I'm going to give this to her, and then she's going to react that with the sodium carbonate, the sodium sulfate, and the potassium iodate. So she's going to run those reactions, and then from that, hopefully she has this information figured out, she's going to be able to realize, oh, that was magnesium that you gave me. So you all are going to pick that. So if I'm working with Grace, I'm going to pick either magnesium chloride, calcium chloride, strontium chloride, or barium chloride, okay? I'm going to pick one of these, not the sodiums or the potassium iodates. You're going to pick one of the 4 going across, okay? Listen to me. When you do the unknowns, you're going to do one of the 4 across the top, not the 3 on the side. You're gonna pick one of the metals. You're gonna put that in, you're gonna put drops of that in 3 well plates. You're gonna give it back to the other group and go here, figure it out, okay? So you're gonna do that after you get this table filled out, okay? Are we good? Got it? Okay, so let's go do science.